So last we left off in part 1, chapter 19 was here. I'm going to move on. Here you can have acylation of amines where you add an acid chloride in the presence of your amine and pyridine, forming the amide bond and your other byproduct. And this reaction is called nucleophilic acyl substitution. The mechanism is as follows. Your nucleophile attacks the electrophilic carbon. Electrons go to the oxygen, forming this tetrahedral intermediate. Then the electrons from the oxygen come down, kicking off the chlorine, forming the amide almost, but it's protonated, and so the pyridine comes, deprotonates it, forming the amide. Acylation of aromatic amines is the same thing. In this case, you're using aniline. Here's an acid chloride forming the acetanilide, and then you can perform further reactions. This is a donating group, so you can do electrophilic aromatic substitution and nitration reaction, in which this is para, and then you can actually remove or cleave the amide bond by hydrolysis in the presence of protonated water. So here's problem 1. How would you accomplish the following synthetic conversion from aniline to here? So if you try to do Friedel-Crafts acylation directly, what will happen is your amine lone pairs will attack the acid chloride and substitute it, forming the amide, which is not what you want in this product above. So what you would do is you would protect the aniline by reacting it with an acid chloride, right? And then you would do Friedel-Crafts acylation, and that will allow the reaction to occur. Para, and then you can hydrolyze the amide bond as such. You can react with sulfonyl chlorides to form sulfonamides. Here's nucleophilic attack, kicking out the leaving group. In the presence of hydroxide, this will then deprotonate, right, forming the sulfonamide. Primary, secondary amines react with the sulfonyl chlorides. So the synthesis of sulfanilamide, it starts off with acetanilide with sulfonyl chloride to generate this product, which then reacts with amine, which will displace the chloride over here, forming the sulfonamide, and then under dilute HCl and heat, cleave this amide bond to form the amide, to form this sulfanilamide. In 1936, sulfanilamide was found to be effective against streptococcal infections, as such, very important. There are other biological activities of sulfanilamides. Here's para-aminobenzoic acid, which is an analog of sulfanilamides, and you can incorporate that and form or synthesize folic acid, which is an essential compound for growth and reproductions. Sulfanilamides cannot be used to make folic acids. Bacteria cannot distinguish between sulfanilamide and para-aminobenzoic acid, so it'll inhibit their growth and reproduction, and that's how it works against streptococcus. Amines is leaving groups, so amines can undergo elimination reaction to form alkenes. NH2 or NHR groups are not good leaving groups because they're very strong bases. Exhaustive methylation can convert the amino group to a quaternary ammonium salt, which serves as a good leaving group because it can produce a neutral amine. So if we look at the Hofmann elimination, here's your amine. You can methylate it to generate the quaternary ammonium salt, and then in the presence of silver, it will deprotonate, leave in the presence of heat, form the double bond, and so it'll form the least substituted alkene. If we exhaustively methylate amines, here in the presence of methyl iodide, this becomes a good leaving group, and this is a good cation to react with. So we can convert quaternary ammonium iodide in the presence of silver and water to the quaternary ammonium hydroxide. The silver iodide precipitates, and this will serve as the base for the elimination for the elimination step. And then elimination is an E2 elimination, so it's concerted and has to be anticoplanar. So it'll pluck off, form the double bond, and kick off the amine that's the leaving group. And so a Hofmann elimination occurs, producing these products. There is regioselectivity in Hofmann elimination. So if we have, for example, butane to amine in the presence of excess methyl iodide and silver oxide in water, you generate the quaternary ammonium hydroxide. Now the hydroxide will deprotonate either here or over, here or here, and then form either the double bond here or over here, and this will leave. So you can generate but1ene or but2ene, and the one that is favored is the Hofmann product or the least substituted product. If we look at the mechanism, if we look along the C3-C2 bond, hydroxide comes off, makes the double bond and kicks this out. This is needed for the anticoplanar conformation is needed for E2 elimination. However, this is not necessarily the most stable configuration. If we look at the most stable configuration, it is not in the appropriate conformation for E2 elimination. However, if we look at across the C1, C2, here is the elimination. And any of the, if you try all the conformation, any of the staggered conformations is suitable for the E2 elimination. Thus, the Hofmann elimination is preferred, or the least substituted is preferred. Important thing to note is that the key to solving Hofmann elimination problems is to find all possible ways the compound can eliminate. Then the one that gives the least substituted alkene is the one that is most likely favored. So here's question 2. Predict the major products formed when the following amine is treated with excess iodomethane followed by heat with silver oxide. So if that happens, here's the molecule. You can have hydroxide pulling this one off, forming the double bond, kicking this one off. Hydroxide putting this hydrogen off, forming the double bond, kicking that off. Or the hydroxide actually pulling this hydrogen off and forming the double bond, kicking that out the other way. So if we look at the possibilities, you have an internal alkene, a terminal alkene, but then an ethylene. Obviously, this is monosubstituted, and it's actually not monosubstituted. It's an unsubstituted double bond, and as a result, this would be favored. Oxidation of amines. So amines can be easily oxidized, even in air. Common oxidizing agents are peroxide or MCPBA. Secondary amines oxidize to their hydroxylamine, as shown here. Tertiary amines oxidize to the amine oxide, shown here. If we want to prepare amine oxides, you can take a tertiary amine reacted with peroxide or benzoic acid. Benzoic peroxy acid, that is. This will generate the tertiary amine oxide, and this tertiary amine oxide, or N-oxide, can undergo eliminations to form alkenes in a reaction analogous to the elimination, otherwise known as the Cope rearrangement. So once you have this nitroso, the electrons will pluck off that hydrogen, form the double bond, and kicked it off, and this occurs in an E2 mechanism. The amine oxide acts essentially as its own base through a cyclic transition state, as shown here, so there's no need for a strong base. If we have a question, it's problem 3. It's asking to predict the products when it's treated with peroxide. What happens? So the first thing happens is the nitroxide is formed, and then elimination can form where you have the double bond over here, or from this methyl group, the oxygen could pluck off the hydrogen and eliminate to form this. This is least substituted. As a result, this is going to be your product. You can form diazonium salts. Amines in the presence of sodium nitrate and HCl will generate diazonium salt, which will then decompose into the carbocation and the nitrogen as gas. So if we look at this, the amine tacks the nitrosodium ion, generating this bond, and then the water will pluck off the hydrogen, electrons will go on the nitrogen. Again, the oxygen will react with hydronium, taking off that hydrogen, and then electrons from water, after it undergoes resonance, pluck off the hydrogen, electrons go to the nitrogen, so that you have this N double bond NOH. Once you have the N double bond NOH, will protonate. This will then have electrons go to form the diazonium salt, shown here. So aryan diazonium salts can be generated. Here is toluene, you nitrate it, and then the presence of iron and HCl, and hydroxide, you can convert the nitrate into an amine. Then in the presence of sodium nitrate and HCl, you form the aryan diazonium salt. And once you have this is a good leaving group so that you can react it to add on any functional. So here are the different types of functional groups that aryan diazonium salts can react with. If you react with protonated water, you generate phenols, CuCl, chlorides, CuBr, bromides, CuCN, nitriles, HBF4, fluorides, Ki, iodides. H3PO2 will actually remove this and deaminate, so it's just going to become the aryl or the benzene, and then you can actually couple another aryl group so that you generate azodiol. Sandmeyer reactions will take the aryl diazonium salt, reacted with copper halide or copper cyanide, to generate the substitution and nitrogen as gas. So here's NH2 converted into the diazonium salt, and then copper chloride to replace the NH2 with Cl. NH2 is being substituted with Br, again converting into the azide and then reacting it with CuBr. Reductive amination, so you can take aldehydes or ketones reacted with hydroxylamine to generate an oxime, and then you can reduce by treating it with lithium aluminum hydride or sodium borohydride molecule, and then generate the amine, the primary amine. You can do reductive amination on secondary amines. Again, start out with a ketone and aldehyde. Here you take a primary amine. This will react to form the N-substituted imine, and then you can reduce again using lithium aluminum hydride or that sodium cyanoborohydride in the previous slide, generating the secondary amine. You can also generate a tertiary amine by taking ketone aldehyde, this time reacting with a secondary amine, forming the aminium salt, and then reducing specifically with this NABH OAC3 in the presence of acetic acid, shown here. This will generate the tertiary amine. So if you're asked as another problem how to synthesize the following amines from the starting materials, N-cyclopentyl aniline from aniline and N-ethylpyrrolidine from pyrrolidine. So aniline reacts with cyclopentanone in the presence of acid to generate the amine shown here. Then you can hydrogenate, and this will generate the product. You can take pyrrolidine reacted with acetaldehyde in the presence of acid, generating the imine, again reduce to generate the product, N-ethylpyrrolidine. You can synthesize primary amines by acylation reduction reactions, in which you take an acid chloride reacted with ammonium. Again, electrons will go, kick up out the chloride, generating the amide, and then you can reduce that in lithium aluminum hydride followed by hydrolysis to generate the primary. You can do the same thing, this time reacting it with acid chloride with a primary amine. Same reaction, I won't show the arrows. Generating an N-substituted amide in the presence of lithium aluminum hydride followed by hydrolysis, generating your second amine. Tertiary amine, same thing, acid chloride, this time a secondary amine. Again, reaction is nucleophilic attack, forming the N-N disubstituted amide, again, followed by lithium aluminum hydride reduction and hydrolysis to generate your tertiary. So, show how do you synthesize N-ethylpyrrolidine from pyrrolidine using acylation reduction. So if you have pyrrolidine, acetyl chloride in the presence of pyridine, you form your amide. Then you treat it with lithium aluminum hydride followed by hydrolysis to generate your product. Gabriel synthesis takes phthalimide anion, reacts it with the alkyl halide via SN2 reaction, and then generating the N-alkyl phthalimide, which then reacts with hydrazine to generate the phthalimide hydrazine and the primary amine. So hydrazine, just so I'll show you one half of the reaction, and this will kick this off, and then the other will do the same thing on this end, generating your phthalimide and then your primary amine. Reduction of azides, so you can take azides and react them SN2-wise to an alkyl halide, generating your azide, and then you can treat it with lithium aluminum hydride followed by hydrolysis to generate the amine. So alkyl halides in the presence of nitriles can do an SN2 reaction and again be treated with lithium aluminum hydride or H2 and catalyst to form an amine. This time one carbon is added because of the fact that the nitrile is there. Important thing to note is that to convert an alkyl halide or alcohol via tosylate to an amine, form the azide and then reduce. To convert it to an amine with an additional carbon atom, you want to form the nitrile and then reduce. Either case, alkyl group must be suitable for displacement. And then finally, we have the reduction of nitro compounds where you have nitro. So nitro group can be reduced by either catalytic hydrogenation or active metal and acid. So this is tin and sulfuric acid. This will generate the ammonium salt, and then in the presence of hydroxide deprotonate to generate the amine. So these are commonly used to synthesize anilines. So this ends part 2 of chapter 19.